I want to begin the whole conversation about counting principles by just asking you a question. You guys ever been to like a restaurant before?
Yeah.
Yeah. You ever been to a restaurant before? Have you ever been to a restaurant that has a prefix menu? Yeah, those are good, right? Okay, so I found one online called Cafe Bisou over here. And so to demonstrate, here's what I'd like you to do, okay? Here's the Cafe Bisou menu. So, it's kind of hard to see, but here, maybe I can zoom in a little bit. Yeah, there we go. Okay, so check it out. Cafe Bisou here. There's 3 courses, prefix menu, $20. Here's the first course. The first course is either soup du jour, which means soup of the day in French, or Caesar salad. I have a funny story about soup du jour, but not today. Okay, second course, you can either have braised lamb, Idaho trout, New York steak. All right. And then dessert is either a flourless chocolate cake or a homemade tiramisu or a trio of sorbet. Okay. Here's your task, okay? Here's the menu. You got first course, second course, and third course, and I'll zoom back out, okay? Here's what I'd like you to do. I would like you to write down your ideal meal. Write it down. Write down first course, second course, third course. Ready, set, go. That's what I want you to do. So we have three contestants. Okay, Kenzie, what did you pick? What's your meal, Kenzie? And I'll do this in black. What did you pick for your first course? A salad. Okay. Then what? The trout. That's okay. And then your third one. What'd you pick? Ooh. Okay. Cole, what'd you pick, dude? The soup. The lamb. And the cake. Okay. And Tess, what'd you pick? The soup. The trout. And the tiramisu against spelling. Okay. So here is the point we're trying to make here. So check this out, you guys. We have this right here is one meal, right? This right here, this is a different meal, right? And then this one over here, this is yet another different meal. So the question that I have for you is this: how many total different meals can be created out of this prefix menu? That's the question I want you to talk about right now with somebody you like. Start this conversation off. Josefa, I heard you guys say something. What were you guys talking about that? What do you think? How many meals total could there be? What do you think? You think there are 56 total meals. Okay, did anybody have a different number they came up with? What did you come up with? You come up with 18. Okay, anybody else come up with a different number of meals we can come up with? Okay, see what I mean about human beings being terrible counters? Kenzie, what do you think? You think it's 56 or 18? Okay, so here's what I mean, all right? There's only one menu. There's only 3 things. We're talking about first course, second course, third course, right? We're not very good at counting. It's hard to keep track of things, okay? That's why this first idea called the fundamental counting principle is so important. It's so basic, but yet so powerful, and those are often the most important principles, okay? The fundamental counting principle simply says this: the total number of ways that something can happen is simply the product of the individual ways that those things can happen, okay? So here's what I mean by that. So think about your meal. Think about it as a sequence, okay? The first thing you do is you pick a first course. Then you pick a second course, and then you pick a third course, right? And all of this is what's called your meal. Everybody agrees with that? Hello? You guys with me on this one? Okay, that's your meal right there. And your meal is a sequence of choices, right? So how many choices do you have for your first option? Yeah, it looks like there are 2 choices. You have a grand total of 2 choices for your first option. How many choices do you have for the second course? Well, you can have the lamb, you can have the trout, or you can have the steak. That's 3. Okay? And then for your third choice, you can have the chocolate cake, tiramisu, or the sorbet. That's also 3. The fundamental counting principle says the grand total ways that these can happen is just multiplying them all together. So you get 2 times 3, which is 6, times 3, which is a grand total of 18 ways we can make this. So it's not so many. Whoever guessed 18, you guys are on the right track. That's the fundamental counting principle. This is box number 2. I have 2 examples, all right? Example A is called what to wear, and example B is called the iPhone passcode. These are 2 examples of the fundamental counting principle actually in action, all right? So let's say you wake up in the morning and you want to get an outfit going for yourself. Okay, well, you're gonna put on I don't know, some pants.
Pants are good.
So pants are good, whatever. So you're gonna pick some pants. You're gonna pick a shirt. Okay. You're gonna pick a jacket.
And a hat.
Oh, you're gonna pick a hat. Okay, I like that. And you need some shoes, right? Some shoes.
No, you don't always wear socks and shoes.
Okay. All right. So here we go, ladies and gentlemen. I love this audience participation. Pants. Huzaifa, how many pants you got? How many pairs of pants do you have?
17.
You think you have 17 pairs of pants? Wow.
I have 2 pairs.
Shirts. Bree, how many shirts you got?
I have 2 pairs of pants.
Wow, Bree's got 15 shirts. Okay, jackets. Caitlin, how many jackets do you have? You have 7 jackets. Okay. Okay, hats.
I have 8 hats.
8 hats. All right, good. And shoes. Kenzie, how many shoes do you have? How many pairs of shoes do you have? 35. Wow, that's an amazing amount. No, that's not right. How many shoes do you have? Wow, you really have 35 pairs of shoes? Okay. Okay, what does the fundamental counting principle say? How many outfits do you have? Holy cow, you have a lot of outfits. Okay, someone calculate that. What would that be? Okay. Wow. You have 400. You have almost 500,000 different outfits. That's an amazing amount of outfits. Okay. Now I agree that not all pants go with all shirts, but still, if you cut that in half, that'd still be a whole lot of stuff. Another example of the fundamental counting principle: the iPhone passcode. All right. How many different passcodes are there? Let's see here. Well, this is a fundamental counting principle problem because what are you doing for each event, right? This whole thing makes up your passcode, right? This whole event is your passcode. You have to push this button first, then this one second, then this one third, then this one fourth, right? These are your buttons. Okay, well, how many choices, how many digits do you have to choose for your very first entry? You have 10 because you could choose 0 through 9. There are 10 different digits, right? So you have 10 different choices for that one. Well, that's also true for the second, third, and fourth. So you have a grand total of, when you multiply these together, because the fundamental counting principle says to multiply them together, we have how many? We have 10,000. There are 10,000 different passcodes for your iPhone, right? Before the fingerprint thing came about, right? But now, how does this change if I say to you that you are not allowed to repeat a digit? Well, you have 10 for the first one, but then you only have 9 for this one. Then you only have 8. Then you only have 7. So if you don't repeat a digit for your passcode, how many fewer passcodes are there? Like, what's the grand total for this one? You only get 5,084, right? 5,040. So almost half, right? So 5,040. So the probability of someone guessing your passcode is hard. It's one out of one of those two things, right? But the probability is harder if you have a repeated digit in there, right? Because there's more of them. Isn't that interesting?
I don't have a passcode, so.
Yeah, now we just have the thumbprint scanners. But anyways, beforehand, this is like what we didn't have before, right? Okay, 2 more examples for you. It's still in the same box. Let's say you're going to take a multiple choice test. The multiple choice test has, I don't know, 5 questions on it, okay? Has 5 questions in and each question, it's multiple choice, so and each question has 4 answers. That has you can pick A, B, C, or D. Okay? Okay, 5 questions, more like a quiz, right? So I have 5 questions. So here's my 5 questions. 1, 2, 3, 4, 5. Here are my questions. And how many choices do I have for each question? I have 4 choices for each question. So I can pick A, B, C, or D, 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 and then finally A, B, C, or D. So how many different ways can I answer this multiple choice test? It'd be 4 to the 5th, right? What would that be? Who's got it for me? Kenzie, got it for me? 1,024. So since there's only one right answer, or per question, right? Then the probability of getting this, of guessing every single one right, is 1 out of 1024. So are those good or are those bad? That's pretty bad. So don't rely on, I'll just guess and get it right, because you have that probability of actually getting it right, 100%. Okay? Kind of crazy. Another example of the fundamental counting principle is airport codes. You ever notice like LAX has an airport code, like SFO, John Wayne I think is SNA for Santa Ana, right? Okay, so if an airport code has 3 spots for letters, okay, and you can repeat a letter, then how many different airport codes are there in total? How would you figure it out? This is a fundamental counting principle problem because it says there's how many letters in the alphabet? There's 26. I have any one of 26 for that choice. And then I have 26 for the second choice and 26 for that choice. So I have a grand total of, I think it's like 17,576. How many airports are there around the world, or at least in the United States? Are there more than that or less than that?
Here, I got you.
I don't know, right? We'd have to ask Google or Siri or OK Google. Important. This is going to be an example of a permutation, all right? So we're going to study permutations and combinations next, and I'm going to give you an example of each one to illustrate the point. Here's the first one. Okay, there's 13 players on a baseball team, and you need to choose a batting order for the 9 players that are in the game. Anybody ever play baseball or softball? And you know how this. There's 9 people in the field. The only people who can bat are the ones who are in the field, depending on which league you're in, right? Okay. So how many batting orders can you form? So the main idea that I really want to get to you across is for a permutation, the order in which we do these things is very important. Very important. Okay? So we have 9 slots to fill. 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Okay? So how many choices do I have to fill my first slot? How many players are on my team? I can choose from any of the 13. Batter 1, I can choose any 13, right? Well, then that means batter 2, batter 1 can't go again, right? So there's 12, and you can easily see what's going to happen here, right? 9, 8, 7, 6, and then finally 5. All right, well, the fundamental counting principle says that I'm supposed to multiply these whole thing in order to get out the total number of ways I can put this sequence together, right? So when you multiply all those together, I believe you get 259,459,200. That's how many different batting orders that we could create from the 9 players that we want to bat of the 13 that are on the team. Does that make sense to you of what I did? Yeah? Okay. So let's think about what we just did here, okay? There's another way that I could write this out. I did this. I did 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and then 1. What if I just wrote them all out, okay? But you'll notice, where did I stop in my permutation? Where did I stop? I cut it off at what number? I cut it off from here, right? So that would be the same thing as dividing by that number. 4, 3, 2, and then 1. You guys see that? Okay. So if we think about it in terms of what we actually did here, this top number is 13 factorial. You guys see that? Okay. And this bottom number here is actually 13 minus 9 factorial, which is 4 factorial. So we have just come up with a formula for a permutation. So let's say I have n objects and I want to permute r of them, means arrange them in a certain way. Then it is n factorial over n minus r factorial. This is going to be a very, very important formula for us to work with, okay? And let me show you where this button is on your calculator really quickly. So, take the calculator out. And we're trying to figure out, from the 13 players, we want to permute 9 of them. So we want 13 P9. So let me show you where it is. So hit 13. And then if we do math, and we go all the way over to probability, and you'll notice I have option 2 is PR, and option 3 is CR. Well, the C we already kind of worked with in the binomial theorem. That's choosing, right? And then the P stands for the permutation. So if we choose option number 2, and then I say, okay, of my 13 players, I want to arrange 9 of them in a particular batting order. Look, we get the exact same number that we just came up with before. All right, 259,459,200. All right, let me give you an example of a permutation here, a classic example of a permutation, right? Let's say you have 7 books for your classes. Okay, how many different ways can you actually put those books in your locker in a particular order? So here's an example, right? Math, science, art, history, English, music, bio, right? I'm just made those classes up. That's different. That's a different arrangement. If I just switch music and bio, the last 2 books, then that counts for another one, right? So the order in which the books are lined up is very important. That's what I'm asking here, right? So how many ways can this be done, all right? So I've got these 7 books. So what am I doing here? This is a fundamental accounting principle problem, right? So how many choices do I have for this slot right here? I have 7, right? How many for this one? No, I only have 6, right? I have 6. How many for this one? I have 5. How many for this one? 4. How about this one? 3. How about this one? 2. And then finally, how about this one? It'd be 1, right? Does that make sense to you guys? Yeah? Okay. So this will just be 7 times 6 times 5 times 4, 3, 2, and then 1. What would that be? Yeah. Yeah, what would we get? Yeah, there you go. 5,040, right? So if we're in the calculator, if we're gonna check this out, right? If I do 7 math over, right, probability, I want to permute 7 of them, all 7 of these things, right? Then I have 5,040 ways I could do it, right? Now, is that the same thing as 7 factorial? 4, option 4. Yes, it is. It's the exact same thing, right? Doesn't that make sense? Okay, I feel like Okay, last box here. Let's talk about a combination, all right? In a combination, the order in which you choose things does not matter. Order is not important. Okay? And we saw earlier the formula for NCR is n factorial over r factorial times n minus r factorial. So this we already have from the binomial theorem. So how does this compare to like the problem with the baseball players, right? So let's see here. Baskin Robbins has 31 flavors of ice cream. So how many 3-scoop ice cream cones are possible? So this is different than a permutation, right? This looks like this scoop is like vanilla, chocolate, and strawberry, right? But if I put strawberry on top, it's the same ice cream cone because I don't care the order in which they come. I just want to know how many different 3-scoop ice cream cones are possible, assuming that each scoop is different, right? Okay. So how many do I have? I have 31 things, right? And I want to combine any 3 of them. Does that make sense? So I don't care the order in which they're stacked. I just want to know how many different 3 scoops I can have, assuming that each scoop is different. You guys with me on this? All right, so we'll compute that. That's very simple. Let's go 31, math, cruise over to probability, go 3, and there we go. Looks like I got 4,495 different ways I could combine any 3 of the 31 flavors. Does that make sense to you? So I got 4,495. So I'm getting 4,495.